We're looking at the massive beating hearts of global trade, marine diesel engines. These towering, multi-story power plants move literally all the world's cargo. But they also pump out a staggering amount of atmospheric pollution. So today, we're decoding the multi-million-dollar machinery designed to clean up that exhaust. And to help us unpack this high-stakes medical drama for heavy machinery, I've got my co-host here with me.
Thanks. Yeah, it's absolutely crucial to understand right out of the gate that this isn't just about bolting a simple filter onto a tailpipe. Engineers are constantly balancing extreme thermodynamics against some incredibly strict environmental laws. It's a massive, fascinating challenge.
Exactly. And to see just how high the stakes are, imagine you're standing in the engine control room of a massive container ship. Now, you might think the most important monitor in that room is the engine speed, right? Actually, no. It's the CEMS display right there on the screen, the Continuous Emission Monitoring System. Let's say you're sailing inside a SECA, a sulfur emission control area, like the North Sea. Suddenly, that CEMS display flashes. Your SO2 to CO2 ratio has spiked over 4.3. So, what happens next?
Well, I'll tell you what happens. Catastrophic fines and port detentions. It's an absolute operational nightmare. Under MARPOL Annex VI, which is basically the international rulebook for air emissions, failing to control your exhaust gas doesn't just get you a little slap on the wrist. No way. It can get your ship legally detained in port and cost the operating company literally millions of dollars. So the stakes for keeping these emission control systems perfectly tuned, astronomical.
Right. And as you can see on this timeline, the regulatory noose has tightened drastically over the last couple of decades. Back in 2000, MARPOL introduced Tier 1 limits for nitrogen oxides, or NOx. By 2011, Tier 2 became the global standard. But look at 2016. That was a real game changer. That's when Tier 3 took effect. For ships operating inside those specific emission control areas, Tier 3 requires a massive 80% reduction in NOx compared to Tier 1. An 80% drop! You absolutely cannot achieve that by just, tweaking the engine a little bit. You need massive, dedicated chemical engineering systems to pull that off. Which brings us to Section 1, the NOx battle. It's really a question of internal prevention versus external cure. So, when dealing with nitrogen oxides, you have a fundamental choice. Do you fix the emissions inside the engine during combustion, or do you clean them out of the exhaust stack after they've already formed? I'm a big fan of the prevention method you see on the left, EGR, or exhaust gas recirculation. This modifies the internal engine thermodynamics. By cooling and feeding a portion of the exhaust gas back into the engine, it dilutes the oxygen. Lower oxygen means a lower peak combustion temperature, which stops that NOx from ever forming in the first place.
Sure, prevention is great, but I'll defend the cure method on the right side of the screen, SCR, or selective catalytic reduction. This acts as a literal external chemical laboratory bolted right onto the exhaust stack. It catches the NOx after it's formed and chemically breaks it down before it ever hits the atmosphere. It's incredibly effective.
But to really appreciate how these systems work, let's move to Section 2, visualizing the invisible chemical war. Take a really close look at the screen as we dive into the unseen microscopic reactions happening inside that exhaust. To understand why these systems are so complex, we have to look at the root disease here, the Zeldovich mechanism. Normally, the nitrogen and oxygen in the air we breathe just totally ignore each other. But inside a marine diesel cylinder, the extreme peak combustion heat and pressure literally force these atmospheric elements to bond together, creating toxic nitrogen oxides. Simply put, the hotter the engine runs, the more NOx it creates. It's like a giant high-pressure pressure cooker for pollution.
Exactly. And that's where my external chemical lab comes in. If we zoom into the chemical injection layer of the SCR system here on the slide, you'll see a three-step process. Step 1 involves injecting a marine-grade urea solution directly into the exhaust stream, which, by the way, needs to be screaming hot, well over 300 degrees Celsius. Step 2, that intense heat causes thermal decomposition, basically turning the urea into ammonia. Finally, Step 3, as the gas flows over a vanadium catalyst bed, that ammonia reacts with the toxic NOx, reducing it into entirely harmless nitrogen gas and water vapor. It is an absolute masterpiece of chemical engineering.
It is a masterpiece until it goes wrong. There's a dark side to this chemistry. What happens if the engine load drops and that exhaust temperature falls below 250 degrees Celsius? Well, the urea won't fully convert. Instead, as you see defined here, it forms ammonium bisulfate. This is basically a sticky, destructive glue that physically coats and completely ruins those expensive catalyst blocks. It drastically drops your emission reduction efficiency and causes massive exhaust back pressure. So that thermal window, it is incredibly unforgiving.
It really is. Now, what about the actual black smoke, the particulate matter? For that, we use a diesel particulate filter. I love the quote on this slide because it paints such a clear picture. Think of the DPF ceramic wall flow monolith like a crowded subway station. Only the small gas passengers squeeze through the walls, leaving the bulky soot behind. That's exactly how it works. The bulky soot passengers are physically trapped. Over time, that trapped soot builds up, and the engine literally has to burn it away by cranking the exhaust temperature over 550 degrees Celsius in a process called regeneration.
All right, moving on to Section 3, scrubbing out sulfur toxins. Now, unlike NOx, which is formed by the extreme heat of combustion, sulfur comes directly from the fuel itself.
Right. If you burn heavy fuel oil with high sulfur content, you're getting SOx out the funnel. Period. To combat this, without switching to ridiculously expensive low-sulfur fuels, ships use what's on this bulleted list: exhaust gas cleaning systems, better known as scrubbers. These are heavy, water-based weaponry systems that literally wash the exhaust gas. We've got open-loop systems, which spray seawater into the exhaust, letting the ocean's natural alkalinity neutralize the acidic SOx. Then there are closed-loop systems, used where discharge is heavily restricted. These use fresh water heavily dosed with sodium hydroxide. And finally, hybrid systems, which can seamlessly switch between the two depending on the specific port restrictions of wherever the ship happens to be sailing.
Which leads us perfectly into Section 4, diagnosing the symptoms, or what goes wrong. Because let's face it, turning textbook theory into practical, grimy engineering reality means stuff breaks.
Oh, for sure. When these systems work, they are absolute environmental lifesavers. But imagine you're a watch-keeping engineer, right? You're walking out onto the deck and you notice a very distinct, pungent odor. You have to ask yourself, why does the exhaust stack suddenly smell exactly like a cleaning closet?
I'll tell you why. The diagnosis is ammonia slip. Remember that urea we injected into the SCR system? If you over-inject it, or if your catalyst has been totally fouled by that sticky ammonium bisulfate glue we talked about, the chemical reaction just doesn't finish. Pure, unreacted ammonia escapes right out the stack and into the atmosphere. It smells terrible, it triggers sensor anomalies, and it basically means your multi-million-dollar environmental system is currently failing.
Let's rapid-fire some more of these mechanical stakes, based on the table on screen. Here's a symptom. The chief engineer notices rapid cylinder liner wear and high iron in the oil analysis. Your diagnosis? The EGR mist catcher has failed, leaking highly corrosive sulfuric acid right back into the engine cylinders. Okay, next symptom. The turbocharger starts violently surging. Root cause there? Your exhaust gas scrubber-packed bed is completely clogged with soot, causing massive back pressure. Last one. Symptom: your scrubber washwater pH drops well below legal discharge limits. Oof, that means the sodium hydroxide dosing pump in your closed-loop system just failed, and you're now literally washing your tower with raw acid. See? The mechanical stakes here are just as astronomical as the legal ones.
Absolutely. Which brings us to the final horizon. The regulatory net just keeps tightening. With the IMO Net Zero framework approaching fast on the global stage, we have to ask, will internal engine tweaks like EGR, external chemical labs like SCR and scrubbers, or entirely new alternative fuels like LNG, methanol, and ammonia win this final battle for zero emissions?
It's a great question. Engineers are walking a tightrope every single day to keep these massive ships compliant and moving. The technology is evolving so rapidly, and the solutions of tomorrow are literally being tested on the oceans today.
We hope this explainer gave you a clear inside look into the incredible engineering happening right now beneath the decks. Keep questioning, keep learning, and we'll see you next time.